So let me talk about splitting field of a family of polynomials. We have talked about splitting field of a single polynomial. It's sort of a minimal extension where you have all the roots of this polynomial. But now I want to find an extension which is minimal and which contains all the roots of a family of polynomials. For example, if you take such a family, all these are polynomials with rational coefficients. If you wanted to solve one of them, if you add the nth root of unity, so zin is e to the 2 pi I over n, let's say. In such an extension, the nth one certainly splits. And you can show, so let's call this guy q sub n. And these are all subfields of complex numbers, right? So if you take q infinity to be the union of all these q sub n's, n equals 1 through infinity, that's the smallest subextension of C you can show where all these polynomials split. So this will be a splitting field for all these polynomials. This is actually a very important subfield of C. It's called the cyclotomic extension. And so it shows up in algebraic number theory in whole hosts of ways. Okay. So that's sort of the thing that I want to talk about, and it's for this purpose it's very convenient to just fix an algebraic closure. So I have the definition of algebraic closure here still. First of all, you say that a field K is algebraically closed if every non-constant polynomial in K factors in linear factors in Kx itself. So we say it splits in K. And an extension K over F is called an algebraic closure of F if the extension is algebraic and the big field is algebraically closed. By going to this one big extension, you're ensuring that all polynomials have all the roots available. And then it gives you a nice playing field, and you can just look at subfields of it. Okay. So here's the definition of a general splitting field. Let's say we have an arbitrary family of polynomials, f1, f2, etc. So I'm just saying fi, I in I. I'm not saying it's a countable or a finite collection, nothing like that. So I have some family of polynomials with coefficients in capital F. Capital F is always a base field, right? An extension K over F is called a splitting field for this family if each fi splits in K, and K is a minimal extension with this property. Meaning what? Meaning that if you take any proper subfield of K that contains F, this is proper, then at least some fi does not split here. Some fi does not split in M. So you have to go up to at least K to factorize all the fi's into linear factors. Okay. So that's the minimality. And now once you know that an algebraic closure exists, which we by the way didn't prove, which is one of these general Zorn's lemma kind of existence proofs, well, if you assume that algebraic closure exists, then you can find a splitting field very easily. All you need to do is you have F, and you are given this family of polynomials. You want to find an extension where all these guys split and it's minimal. Well, first go to the algebraic closure. In there, all polynomials split. So all the roots of fi's are available in f bar. So just take the subextension of f bar obtained by adding all roots of all the fi's in f bar. That's what I'm calling K here on the left in this remark. So if you take that guy, it's clear that all these polynomials are going to split here because they do split here. And how do you factorize them? By taking x minus one root times x minus another root, etc. But all those roots are already available in K. So they all split here. On the other hand, if there is an extension where they all split, they meaning these polynomials, if all these polynomials split, then it has to contain all the roots. So So in fact, what this argument tells you that K is the unique subfield of F bar that is a splitting field of all these polynomials. So once you fix an algebraic closure, it's unique in a much stronger sense. There is just one subfield of F bar, which is a splitting field for this family. Okay. And this actually implies that if you take any other splitting field, not necessarily inside this algebraic closure, then it's also isomorphic to this K. So that would imply that splitting fields are unique as an extension up to isomorphism. So what I'm saying is we have this K, which is a splitting field, for the family. Let me give this family a name rather than writing script F or something. So this is a splitting field for this family script F. Let's say this is another one. Now this is an algebraic extension. If you have an algebraic extension and something that is algebraically closed, we saw last time that you can embed it in the algebraically closed thing. So now if you take the image of this sigma, that's a subfield of F bar. And by definition, M is isomorphic to sigma M because it's embedding, so it's isomorphic to the image. Now sigma M and K are two splitting fields for this family inside F bar, you can show. So they're actually literally the same. So that tells you that M is isomorphic to K. So any other splitting field is isomorphic to this particular one. So any two of them are isomorphic as extensions. So this shows you the existence and uniqueness of splitting fields of general families of polynomials. And I think this is a decent example to keep in mind. So the other thing I want to say is this characterization theorem. Because this is a characterization of splitting fields. Because this would become very relevant in the later development. So let me explain what this says, drawing a diagram. So you have a field F, you have an extension, algebraic extension, and you're asking when is this extension splitting field of a family of polynomials? And before we answer, let's fix an algebraic closure of F containing K. And how do I know there is such a thing? Well, you just need to fix an algebraic closure of K. Algebraic over algebraic is algebraic, remember? So if you fix an algebraic closure of K, that's going to be an algebraic extension of F, which is algebraically closed. So it's also going to be an algebraic closure of F containing K. Okay, so we can fix such a thing. Then there are three statements that are equivalent, A, B, and C. B says that K is a splitting field of a family of polynomials in Fx. C is easy to understand. It says that every irreducible polynomial that has a root in K actually splits in K. So if you have a polynomial in Fx which has one root in K, then all the roots are already in K. This says if some polynomial, that's how I want you to remember this statement, if some polynomial has one root in K, then it has all roots in K. So if it has to split, then that better be true. Okay. And A is the one that I'm actually want to focus on, because that's the condition that's going to become relevant later on. And it's kind of abstract. It says that any embedding of K in F bar fixing F is actually an automorphism of K. So if you write the extension here again and take any embedding, which means injective ring homomorphism from K to F bar, it really means non-zero ring homomorphism from K to F bar, fixing F pointwise, then it actually gives you an isomorphism from K to K. This is very, very strong. You see, any non-zero ring homomorphism is all that I need to assume, because once it's a ring homomorphism and it's non-zero, it's going to become injective automatically because the field has no non-zero ideal. So any such thing actually gives you an isomorphism from K to K, which means there's basically in F bar only one subfield which looks like K. It puts some very strong condition on the subfield structure. Okay. The proof of this would depend on this lemma, which we will prove next time, that when you have any algebraic extension, so the lemma up here, if you have any algebraic extension and you take any embedding from K to K fixing F pointwise, then it's actually an automorphism. And for the proof of this, the finite dimensional vector space business will come into play again, so it's rather cute. And you see, once I assume this lemma, I can prove C implies A quickly. Let me do that and stop, maybe. So let's just do C implies A, assuming this lemma. So you take K to F bar, some embedding, fixing F pointwise, sigma restricted to F is identity. And you take an A. First I want to argue that sigma takes K inside K. K is actually sitting inside F bar, right? So I want to show that sigma takes K inside K. So it takes some A, which is not in F maybe, and it has a minimal polynomial, call it Px. But then if you take sigma of A, that's another root of Px, because if you write P is as some, I don't know, Ci x to the I, the Ci's are in F. So Ci A to the I is 0. That's what A is a root of this means. Now if you apply sigma to this, you just get Ci sigma A to the I equals 0. The Ci's are in F. Sigma fixes F pointwise. So the Ci's do not change when you apply sigma. So that tells you that sigma of A is again a root of this polynomial. But now condition C tells you that if you have one of these roots in K, then all the roots are actually in K. So sigma of A is in K as well. So that means if you take any element in K, sigma of that lands again in K. That tells you that sigma takes K inside K. But now this is an algebraic extension, and this lemma up here tells you that any embedding from K to K is actually an isomorphism. Okay. So that's how this implication C goes to A follows from this lemma. We'll prove the lemma next time.